I stop speaking by 4. Maybe if Carlos is here or whatever, we are done by 4:20 the latest, and we're all going home happier tomorrow. Is that okay for all of you? Okay. So tomorrow we anticipate of 30 minutes the afternoon class. All right?
Okay.
Okay, so let's get back to Carlos.
Okay. So I'm just going to continue where we left off yesterday because I didn't manage to finish the statistical review that we have started. And so I would like to just complete that. And I left 2 exercises on Fabio's hands, and he will hopefully upload them to the website briefly. One of the exercises is basically I construct for you a little, I give you a little data set, I give you a model, and I make you compute the credible regions and have estimators using Bayesian techniques, and then I make you do the same using the frequentist techniques. So that's one exercise, and the other exercise is a neutrino source search exercise. So I give you the positions and errors of the high energy neutrino events we have observed. I give you the Hawk gamma ray catalog, and I ask yourself, are these 2 things correlated? And so hopefully you will find those entertaining. Okay, so what we have left it off is that we are starting to think about the frequentist approach. And so in the frequentist approach, remember that the parameter we're trying to estimate, let's say they have an observable that follows, let's say, a Poisson distribution. The Poisson distribution has a parameter. And so if I want to figure out the preferred values of this parameter, in the Bayesian case, this parameter is thought of as a random variable. And then I can do what we did yesterday and compute the probabilities with respect to the random variable. In the case of the frequentist case, this lambda is a number, and this number is fixed and is unknown. So in order to do that, we need to introduce something that was called a test statistic. Yes. And the test statistic is going to be a random variable. And because it's a random variable, it has probabilistic, it requires probabilistic properties. And I'm basically going to try to construct, using these random variables, ways to figure out where these parameters could be. So yesterday I had introduced the chi-square random variable, sorry, chi-square test statistic. Yes, so we have some continuity here. The chi-square over some amount of bins was defined as the sum over the bins. Keep using the wrong symbol. Depends on my model parameter. And the error. So, sorry. I was telling you that the error here typically is going to be a combination of statistical error and a systematic error, systematic uncertainty. So this is very much going to be experiment dependent, but the statistical uncertainty, you can say that because the statistical uncertainty comes just from a counting experiment, this is just going to be equal to mu I stat. Sometimes in some texts you will see that, yes. Oh, yes. No problem. Some texts you will see that the chi-square definition introduces statistical uncertainty, not as the expected number square, but the observed number. Instead of mu I, some people use xi. So this definition that uses the expected mean is Pearson's definition, and it's a little bit more stable. Okay, so I was telling you yesterday something that is very important is that once I have a test statistic defined, I need to compute or establish what is the test statistic probability distribution. So how is that going to be? So first, you are going to assume there is some reality. Let's call it that. Let's call that theta 0. And from that reality, one can produce, call this the real model. I can produce pseudo experiments, pseudo data. So for example, how will you do that? Imagine that I have my counting experiment. So my counting experiment is going to have 3 bins. Let's say this is the energy that's observed. And in these 3 bins, this model predicts in this first bin, let's say 1 event. In the second bin, it predicts 1.5 events. It doesn't need to predict an integer number of events. It can predict a non-integer number. And here it predicts, let's say, half an event. Okay? So that is my prediction according to this particular model point. So one way that one can construct pseudo data, we call that, pseudo data according to this particular prediction is the following. So in each of the bins, one can assume that the number of expected events, if this is what really is going on, is going to be a Poisson distribution, which mean is going to be this value. So basically here you have the mean according to this hypothesis for the first bin. Here is the mean of the according to the same hypothesis for the second bin, and expected for the third bin. So then what you do is you say, this is going to be, when I generate my pseudo data, my bin content on my first bin is going to be, it's going to call it x. On my first bin is going to be a Poisson variable with lambda 1, theta 0. And you do that for each of the bins. So you can do that very easily now in the computer and in Python. Basically, we'll ask the computer, tell me, generate me Poisson numbers or Poisson realizations, which just mean given by that, and that in each bin. And doing that many times, you will then get a set or an ensemble of possible realizations that have been generated according to these 3 values. So for example, if you run it once, maybe the first time you get like no events in the first bin, you get 1 event in the second bin, and maybe 1 event in the third bin. And you repeat this many times, and you're going to generate basically a collection. Right? In this case, there are 3 bins, so I get my number in my first bin, my number in my second bin, my number in my third bin, and so on and so forth. And these are going to be pairs of 3. Okay? So this is going to be an ensemble of basically pseudo data that's been generated according to this particular real assumption. Good. So now, once you have that, once you have produced this pseudo data, you can try to estimate your test statistic distribution. So what you will do operationally is, this is my test statistic. For each pseudodata realization have generated, I will evaluate my test statistics. So I evaluate my test statistic now at some hypothesis theta. Note that this hypothesis is now not the same as my generating hypothesis, can be something different. And I will evaluate the test statistics at each of these fake realizations of my experiments. So when you do that, for each combination, you're of course going to end up now having a list of numbers, right? So there will be a first number, a second number, and so on and so forth. And then you get to histogram those numbers. And let's say that looks like that. This is a histogram. I think it may be more obvious that this is a histogram. Yep, so that's how it looks. And so this will be the test statistic distribution for hypothesis theta, given that in reality, nature had chosen hypothesis theta 0. And like I was saying yesterday, right, different hypotheses are going to have different inclinations. This theta 0, 1. Then you could have another one that looks like that, theta equal 1, so on and so forth. So the p-value is the probability that the data, or how likely this particular outcome is the particular observed outcome, the particular outcome that's observed is, and it's going to be equal to the test statistic, the probability that the test statistic is greater than some observed test statistic value. So similarly as you did, you evaluated your test statistics for each of your fake experiments, in reality, you're going to have a real experiment where you're actually going to say real counts. And so the real counts are going to get some numbers in each of your bins. So you will evaluate your test statistics on the real data, and that's going to give you the observed test statistics. Okay? And so in this line here, I generated my test statistics always with the null, but I expected this line, sorry, these lines are confusing because it was a semicolon. Let me just use yellow. Okay? So when theta is 1, underlying of all of this is that some underlying hypothesis, so that one here. But you can see that in this case, theta equal 1 has a very long tail. So the value of the test statistic that I got is a typical value. It's found somewhere within your distribution. Whereas the case of theta equal 1 produces a test statistic distribution that's much more sharper. And that means that smaller p-value makes the hypothesis less plausible. It does not make the hypothesis less, it does not mean that the hypothesis probability is small. As we said yesterday, the only way you can actually establish the probability of a hypothesis is via an inference process. An inference process always requires prior knowledge of your degrees of belief of your hypothesis. But the p-value is an indication of how unlikely this TS observation is given, this TS observation is given the expected test statistic distribution. Okay. Another statistic that's very common is to use the likelihood function as a test statistic. So that is what we're going to use most of the time. It's often very good to normalize the likelihood. So another TS that's defined is called the deviance. And so the deviance is a test statistic, which is defined as -2 times the log of the likelihood function of my model minus the log of the likelihood function sub upper S. And what this is here is something that's known as the saturated It's something that's called a saturated likelihood. The saturated likelihood is the best possible likelihood that you can construct given a particular observation. And for example, and is defined as, so the best thing I can do if I have given a set of observation is to make my model just match my observation. So it's equal to the log of the probability that I saw X, given that my expectation was also X. Okay? I mean, you cannot do better than that. So in the case, if I had this particular set of data points, my saturated likelihood, how we calculate it, I will calculate the probability of seeing 0 given that I expected 0, the probability of seeing 1 given that I expected 1, and the probability that I saw 1 given 1, given that each of these was a Poisson process. Okay. There is something very nice about the deviance is that under certain conditions, namely when the number of observed events per bin is more than 20 counts, the deviance is going to follow a chi-square distribution with k degrees of freedom, where k is the number of bins. It's the number of bins. Okay? What does this mean? That means that if I decide to use my test statistic to be the deviance, so I pick that, okay, and I am in the large statistic regime, so the number of, let's say, the number of events per bin is more than, let's say, approximately 20 or so. That means that I no longer need to compute my test statistic distribution. What this guarantees you is that your test statistic distribution is just 1 given by a chi-square of some number of degrees of freedom. So this theorem here basically allows you to skip the very expensive process of making this Monte Carlo to construct fake realizations. Okay. Good. So very often we would like to be in that situation, if not always. Good. So now let me go to the 3 problems that we also solve in the Bayesian case. And the 3 problems are parameter estimation in the frequentist case. So that is, given that I have a model, I want to know what is an estimator of my parameter lambda. Let's go here. And so parameter estimation, the estimator is defined to be, it's the value that minimizes my test statistic. Okay. So for example, if my test statistic is the deviance, or just the likelihood itself, this theta, because this value is a constant that's independent of theta. So theta is it's on here. This value is equal to the arc mean for 2 theta. So I get minus 2 log likelihood. Obviously, minimizing this and minimizing that with this constant is the same. And this is, of course, the same as that. And this is known as the maximum likelihood estimator. or for shorthand, MLE. Okay? Namely, typically you will construct your likelihood problem, and then the maximum of your likelihood, because of course these are max, this 2 is irrelevant here. The maximum of your log likelihood is known as the maximum likelihood estimator. And the maximum likelihood estimator is an unbiased estimator. Okay, so this is basically the equivalent in the frequentist case to the map. Remember that the map was the value that maximizes my posterior. The maximum likelihood estimator is the one that maximizes the plausibility of the model. Okay, now there is the issue of confidence interval construction, which I'm going to cover very briefly because in astrophysics people don't seem to use that as much as in particle physics. So this is the fact that, I would like to provide an interval that will give me some more information about my parameter points. And let me say something that it's very often a source of confusion. So when I say, I'm going to define this precisely in a minute, but often you will find a plot. Let's say this is flux, this is energy or so, this is 1 point. And I show it like that, and I tell you this is the 95% confidence level interval, right? That contains the flux of my source or whatever I'm showing here. So often people read this as thinking that the true value of the flux at this energy is contained inside this interval 95% of the time. This is incorrect. So this is only true for the credible region, right? So in the credible region, I am talking about the probability of my flux or what I'm trying to infer. And for a credible region, the interpretation is that the true value is most likely inside that region with 95% probability. A confidence interval does not mean that. And it cannot mean that because frequentist statistics does not make statements about the true properties of the model. It makes statements about the probability of the data given the model, and it makes a statement about my estimators, which are random variables, and it makes statements about my confidence intervals, which are also random variables. So the correct interpretation of this is that if I do 100 experiments, and I follow the procedure I'm going to write in a minute, 95% of those intervals will contain the true value. This statement sounds very similar to what I said earlier, but the emphasis is different. What I'm telling you is that the probability that the interval contains the value is 95%. Not that the value is contained by the interval. Okay? Because what is a random variable is going to be the interval. Okay? Because the interval is going to be constructed out of my test statistic. So it's a subtle point, but it's an important point. And often people misread this. So people often, when they look at a plot, they have their mindset is based in a Bayesian mindset, right? They're trying to think that these are the true quantities. In reality, this is not the case. Okay. So a confidence interval is such that, let me write you first. I hope you guys remember, but let me write you first how we had defined the credible region so you can see the analogy between them. So in a credible region, I had that it was a region that satisfied this condition. So it was an interval that integrated my posterior, gave me 90% of the probability, or any alpha percent. That is a credible region. Now let me show you what a confidence interval is. Okay. Technically, this is a confidence belt, but we'll get there in a minute. So of course, this doesn't make sense. Doesn't exist here. But this exists. I want that. I want to find two values of my test statistic such that they contain 90 or alpha 1 minus alpha % of the probability. This does exist because TS is a random variable. And that is equal to the integral the PDF of my test statistic this is the, and here I'm going to put semicolon theta. Okay? So remember that the distribution of the test statistic depends on the model that I use to generate the distribution, right? When I produce my fake experiments that allow me to construct my pseudo data, I need to assume some particular reality. The reality is then going to infer my test statistic distribution. So this distribution is in general dependent on your model. So what should be clear is that this equation cannot be solved because it has two unknowns and I only have one equation, right? I need to figure out what TS1 is and what TS0 is, and I only have one condition. But this is the same problem we had already in the credible region, remember? That I need to define a prescription how to add points into my credible region. And the credible region, how we add them, we add the points from the highest posterior to the lowest posterior. So here we need something. So there are three common choices. So if you are going to quote an upper limit, so I see my observation is not strong enough of my flux, the choice is make TS0 equals 0, right? And then this problem just becomes the probability that my TS and TS1 is alpha. Okay? So you want to find the value of your TS such that the tail of your distribution is alpha. So that will be a one-sided upper limit. You can also do a lower limit. And that choice is and if you're not actually putting a limit, but you're making a measurement, you want a two-sided interval. And in that case, you make this choice. Okay? And this is going to completely then define your confidence interval. Once you make this choice, or this choice, or this choice. So I'm not going to go to the detail that, there is a problem here because once I need to look at my data first to see what kind of result I have in order to decide in what scenario I am. So if I look at my data and I think, no, this doesn't look like I have a very large flux, I think we should quote this as an upper limit. Then you do this prescription, get your upper limit. But maybe, another person says, that clearly looks to me that it's a real flare, it's a real observation. I think we should quote an observation. So you see, you can play among these definitions and you get different answers. So this is known as the flip-flopping problem. And the flip-flopping problem is bad. The good news is that there are prescriptions to go around the flip-flopping problem. The normal prescription to go around the flip-flopping problem is called the Feynman-Cousins construction. I'm not going to go to the Feynman-Cousins construction because we will run out of time. But in the references I gave you the first day, you can find the reference to the Feynman-Cousins construction. Okay. Good. Okay. Now, let me go to the model selection piece. So I'm going to rest here. So now, imagine I have two models. So this is the third type of problem that we're facing, the model selection problem. Right? So now I have to do this model selection. So one model can be, for example, model 0. And my alternative model, let's pick our usual suspect. Let's say that it depends on the Dark-matter cross section. Fabio is talking later. Okay. So this is the easiest case of model selection is when the hypotheses are known as nested hypotheses. What does that mean? The hypotheses are said to be nested. This is standard model, sorry. Are said to be nested if there is a parameter, or the parameter of my alternative model has a choice that makes it my first model. In this case, it's possible because if I make my cross-section equal 0, then M1 just becomes M0. Okay? So in some sense, M1, which is, just to be clear, the standard model plus dark matter, right? If I decouple my dark matter, then I go back to the standard model. So in the case of nested hypothesis, there is a lemma called the Neyman-Pearson lemma. That tells you that the most powerful test statistic you can construct to differentiate between two nested models is lambda, which is the ratio of the likelihood of the alternative model divided by the likelihood of the null model. Okay? Because these likelihood ratios are going to be the ratio of small numbers, typically what people do is they use a test statistic, which is equal to -2 the log of the ratio of the likelihoods. So this sounds a little abstract, but let me put this down in terms of neutrino source searches, which is the exercise that I gave you in the website. So let me just go directly to this point. So suppose that I have the following problem. So one model is going to be event. Okay, so one model is that the sky is full of isotropic event distribution. That means that neutrinos are just coming in a kind of a bath. The alternative model is going to be, there is going to be an isotropic event distribution, but there is also somewhere in the sky a neutrino source. Okay? So this is a typical case of interest. So how will we, or let me just tell you exactly what I mean by this. So imagine that we live in a one-dimensional world. So this is my, let's say this is the right ascension of events or direction. In reality, this of course has 2 dimensions, but the model 0 is that all of my events within my sky come out equally likely in each direction that I look at them. That's how that looks. Model 1 is that in reality, the directions that they come is like that, where this is actually the position of my source, right? So I'm trying to distinguish between that and that. Okay. So I'm going to call this the background, because I don't really care about this flat distribution. I care about that spike. And I'm going to call this the signal. Okay? Good. So I'm going to have to construct a likelihood problem that allows me to differentiate or use the data to test M1 versus M0. And let me be more specific. My hypothesis M1 is that not only there is a point source, but that point source, is sending me at least n sub s, so n signal neutrinos. Okay? So let me establish some notation. Good. So say in my experiment, n is the total number of events that are observed. Okay? N sub s is a total number of expected signal events. Okay? Good. So now I can construct the likelihood of one of my events. So the likelihood okay? So the probability that this event happened given model 1 is going to be that this event was a signal event plus the probability that this event was a background event. Note that here, in these conditionals, it's not explicitly written, but of course, this is signal, comma, M1. We're under the M1 model scheme here. I'm just simplifying the notation. So the probability that, so now I have my sky, which, because I cannot draw easily in multiple dimensions, my sky is just going to be a line, right? So my event, this is my event, so it hit here, okay? So in reality, my signal typically is going to have some distribution because detectors are not perfect, so they're not points. So the probability that an event, let's say this is my signal, that an event is a signal is going to be 1, the chances that I get the event. So I have total observed n events, and I expected only n sub s of those. That's that fraction, just picking 1, times the probability that it actually is associated with this signal shape, is I just call it signal at the direction of the event. Okay, I'm just going to call this d vector for direction. Now the probability that the event is a background is going to be, well, if I have assumed there are n sub s signal events, then there are n minus n sub s background events. And thus, this is 1 minus n sub s over n, the chances of grabbing one background event. In the case of the background, I'm going to assume that my background shape is just flat. Let's just be like that. Good. So now, so now I can construct the likelihood of my data set. And now let me be more specific. I already defined my parameter of interest, which is ns. Let me just write that likelihood of ns. Okay. It's going to be equal to, well, it's the likelihood of one of my events. But I have observed n of those, and they're all independent observations. And then it's the product of this probability over all the observed events. Okay. Good. So that's the likelihood function that is known as the unbinned, let's say, point source likelihood function. So now I want to do a test where I am able to check if I'm rejecting M0. So the recipe tells me construct this test statistic. Okay. So my test statistic is going to be equal to, well, I have two hypotheses. One is, let me just write this in redundantly again. This is in symbols, and this is my first hypothesis. This is my second hypothesis. Okay? So the test statistic that's appropriate is equal to 2 times the log of the likelihood, sorry. Okay? Because in the first model, I just have that ns is equal 0, so I can just use that. In the alternative model, I really don't care what ns is. I just care that you are going to find anyone that's not 0. So I maximize of that, all my observed ns. Ns is unknown. Okay. And what is neat about this definition is that you can rewrite this as the maximum. I'm going to put a 2 in front just because it's so. So now here, I'm going to do a log of that. So the log is going to change this product into a summation. Like that. So it's the sum of the log of this, and it's the log of this divided by the likelihood when ns is equal 0. But note that when ns is equal 0, this term is just gone, and you just get b. And so then this becomes I'm using x. No. So the test statistics in the end, it turns out that only depends on the ratio of the signal to background shapes in the sky. So in the exercise that I have given you, you will find that I have provided you with a list of the events. So you know the directions of each of your events in the sky. The background is going to be isotropic in a sphere. That means it's just given by 1/4π. That's it. And from the signal PDF, what I have given you is it's a function that measures the distance between your event and some catalog source. Okay, so my position. And that basically is a two-dimensional Gaussian. It's not exactly a two-dimensional Gaussian because a Gaussian on a sphere needs to get slightly modified. So that's actually known as a Kent distribution, but you will see that in the notes. Okay. So typically, if you get, using this definition of the TS, a TS of 0, or close to 0, is such that it means that it is background-like. So the M0 is reinforced. Large values of the TS, though, will start increasing the likelihood that M1 is true. Okay. But the question is, at what point do I actually say that I'm rejecting, or I think that M0 is unlikely? For that, you actually need to compute the test statistic distribution according to the M0 hypothesis. So I'm going to tell you that in a minute, but just to complete the likelihood definition functions, just a couple of details that may be interesting for you. In this construction here, these S's and these B's are only spatial PDFs, so they only depend on the direction. You could say, I have actually know that my source has some particular energy dependence, and then you could define, for example, that the source, the signal PDF, is actually has a spatial piece, times something that could be, for example, depending on the neutrino energy and depending on astrophysical parameters, say the spectral index. And your background PDF could be, again, just the 1/4π, so that's the spatial piece of that. But we know the background, for example, in S-cube is atmospheric neutrinos. So you know the probability of seeing an atmospheric neutrino. Okay? So use that. Another thing that's interesting is people often do not want to look at a single source, but as lists of source classes. And for that, they look at a catalog. That requires a slight modification of this formula here, or rather, sorry, the likelihood formula. So the likelihood for a catalog search is very similar. You just get a factor a little lengthy. These summations ends here. This is I, this is C. Where now in my sky, sorry, my sky is a line again, I now have multiple sources, each sources indexes by from C0 to C1 and C2. So this now is a two-dimensional Gaussian that measures the position between the event I and the source C. And then you can proceed with the same definition of the test statistic analogously. Okay. So the last point I want to make, so you can do your exercise, is the fact that is the fact that in IceCube, we have a very convenient way of generating the test statistic distribution of the null hypothesis. And the reason is that IceCube sits in the southern hemisphere, in the geographical south pole. So the Earth is rotating like that. And like we were saying earlier, the effective area does depend on the declination angle because of, one, the cuts that we apply, but two, because of the Earth absorption, right? So there's not the same efficiency from here than there. But within a given declination band, as a function of right ascension, so in the azimuthal direction, the acceptance of the detector is the same. That means that the IceCube effective area, if I plot it as a function of right ascension for a given declination band, is actually a constant. And this is very neat, because imagine that I observe a set of neutrino events. They come from the sky. If the null hypothesis is true, so if the observation is isotropic, that means that they are equally likely to come from any right ascension. So this, the efficiency of my detector, and my null hypothesis distributions are the same. So what we do to compute the test statistic distribution is a very simple process. And this process is known as scrambling. Right. So what we do is we take our events. So an event is going to be for me some declination and some right ascension. That's my event's position. Okay, so I have a list of events. And for each of my events, I fix my declination, but I pick a random uniform right ascension between 0 and 2 pi. Okay, so I just move it. It was, let's say, it was detected at this declination. Let me draw it in a square. This is right ascension. This is declination. Say these are my events. Like that. These are the ones I have. I take that event, and I just move it randomly in right ascension. So instead of it being here, I pick a random number, and now it's here. I do that for each of my events, but keeping the same declination. What results of doing this is that I have generated an artificial sample that is isotropic in the sky. Okay? And that's great, because that means that unlike the earlier cases when I was telling you, you have to know your efficiency, you have to do Poisson realizations and so forth, you do not actually need the IceCube Monte Carlo to construct fake realization of your events. You just need the events, and if you move them uniformly in right ascension, that will look like generated according to the isotropic assumption. So basically what you do is, and this is described in some detail in the exercises, you are going to basically take the list of events, which are going to be like 60, and you're going to make fake event lists doing this scrambling procedure. And then for each fake event list, what you have to do is calculate your test statistic. So again, so the test statistic is going to be this one here. Well, this one, but modified with the sources. So that's this one there. So for each event list, I will compute my test statistics. So I take my event, I scramble them in right ascension, compute the test statistic, get a value. Then I do repeat this process. And when you do that, you're going to get the distribution according to this statistic. And then you're going to get this distribution, and then you're going to just calculate your test statistics on the real data, so the unscrambled data. And that's going to be the TS observed So this will be the unscrambled. And this area here is just going to be the p-value of rejecting the M0 hypothesis, okay, in favor of F1. Good. So I hope that you guys find time to try this in the next days. It's only today and tomorrow. But this is how you do it operationally. Okay. So I have 40, 30, 20, 25. 20 plus question. Okay. Okay, why don't I skip this? So the next thing I wanted to show you is a brief derivation of the neutrino oscillation formula, but probably that's not necessary at this stage. So regarding neutrino oscillations, I'm not going to derive the oscillation formula because there's no time. But for neutrino oscillations, if somebody wants to look at the derivations, there are two papers by Evgeny Akhmedov that are good. One from this year, actually it's a summary. It's a pedagogical summary of neutrino oscillations. And this is a more involved discussion. But the bottom line is that neutrinos, like I was saying yesterday in my talk, are going to be able to change flavors. And the flavor changing probability is going to depend on the so-called neutrino mixing elements. So the neutrino state in a given flavor state is going to be a superposition of the neutrino mass states. And this superposition is controlled by these matrix elements. And these matrix elements are often parameterized function of the neutrino oscillation angles. But what's going to matter for us is that the average neutrino oscillation probability from going from a flavor alpha to a flavor beta of an astrophysical neutrino is going to be given by the sum over the mass states or the mass indices of these matrix elements. Okay? So the probability that neutrino changes flavor as it comes from the source to us is only going to depend on how the neutrino flavor states get decomposed as neutrino mass states. Okay. So now I just wanted to show you very fast the status of neutrino flavor measurements. Pause here. See. Let's see if this works the first try or not. Maybe. Oh, it's just of the. Oh, what's that? So some things I had to skip. I prepared some slides on the unfolding techniques for neutrino observations, but that will probably require some time to do, but I will put the slides onto the big slide discussion. It's not possible.
It's lunchtime, so maybe we can find
We can attempt it ourselves. Maybe this guy. Not quite. No. I think it's.
This was working for this one, maybe.
Oh, I think that one is. I think the projector is off. That's the problem.
Yeah. You're an experimentalist.
Okay, that may not work. Oh, maybe it does. It's an HDMI. It's more or less happy. Oh. Good. Now I just need to find the proper screen. That's the wrong tab. Is this coming up? No. Oh, there we are. Oh, good. So we're here. Okay. Oh, maybe. Great. Solved. Okay, so this we did. So this is a discussion we had on Tuesday or Monday about unfolding and not unfolding. So I'm not going to cover it, but basically I prepared some slides so you can look later of seeing how this works. And the nice thing about it is that there are some references at the end that will tell you how to do it later. Okay, so I just want to briefly cover the issue of what do we know about neutrino flavor mixing. I talked about that yesterday in the colloquium, so I think this will be brief. Like I was saying yesterday, we typically organize sources by how the neutrinos are produced. So you're going to have these pion sources, then you have these muon damped sources, and these neutron sources. These are the most popular ones. So this one will require large magnetic field, so the muon will radiate energy. So we organize them by neutrino flavors. So we often talk about them like this. This just means that you have twice the amount of muon neutrinos and electron neutrinos and 0 tau neutrinos. Neutrinos are going to produce in some initial combination of flavors. That depends on your model. And then those initial flavor combinations are going to get mixed. And the mixture of those is going to depend on these matrix elements that we know and measured at Earth. And that's going to give you an observed flavor combination at Earth. Because this is an average, basically, over the distance, once you observe a neutrino, there is no way you can figure out the initial neutrino flavor state. In the standard model, the expectation is that the observation of flavors at Earth is basically equal amount of each of the flavors. You can have some deviation from equal flavor composition, and that deviation is because of how you pick your standard source scenario and what's the error on this P. But the deviations are not going to be large. Typically, you're going to end up here unless something really weird happens. Okay, so this is the flavor triangle. I think I explained this yesterday, so I'm just going to skip this. Okay, but I will tell you that if you knew nothing about neutrino mixing, you do know that there is some amount of conservation of neutrino flux, and that conservation, this is called unitarity, constrains the possible allowed regions of neutrino flavor for a given neutrino flavor state. So for example, if I have a model that is mostly a pion production model, that initial composition is going to be 1 to 0, and the only allowed region that basically preserves neutrino number is inside of this yellow band. So anything outside of this yellow band will imply that you are not inside the pion scenario. Similarly, the neutron models live in this corner. The muon DAM model lives in this upper corner. And like I showed you yesterday, you can actually compute these probabilities more accurately, and you get that you have to be in the center, as advertised earlier. This is going to flash because of time. But that composition of neutrino flavors can be translated into the track-to-shower ratio. Remember that IceCube basically, to first order, sees long tracks, and the tracks can be because of muon-CC interactions, or sometimes because of taus. So for each of my decay models, let's say the pion decay, I can compute the expected track-to-shower ratio. And so this is a phenomenologically derived formula, and these coefficients are the first order just derived from simple arguments, like, for example, the ratio of charge to neutral current cross-section is like 2.5. The ratio of the amount of tracks that a tau produces is 18% of that, and numbers like that. So you can look at this paper here. But basically, the number of showers can be approximated as the number of observed showers, let me be clear, can be approximated by this combination here. Is a phenomenological fit to those, and this is the flux of electrons, flux of muons, flux of taus. The number of tracks is basically only a flux of muons. So you can see that for a pion scenario, you're going to end up a little below, or in the middle between 20 to 30% track-to-shower ratio. In the neutron decay modes, so you start with a new source, the number of expected tracks is going to be less than 20%, so let's say 15%. So by trying to measure the track-to-shower ratio, you can already get an idea of these sources. And the width of these distributions is just given because of the uncertainties in the oscillation parameters. We can go a little beyond classifying things between tracks and showers, and I talked about that a little briefly, but let me just give you a little more details on that. So basically, we have three kind of topologies: the cascade topology, the track topology, and the double cascade topology. So we call something a double cascade when the separation between the first energy loss and the second energy loss is more than 10 meters. And we use this as a signature of tau neutrinos. So in the latest iteration of our high energy analysis, we have actually seen two events that are classified as double cascade events. We call them event number 1 and event number 2. Event number 1 is a very old event. It's actually a big bird. And event number 2 is a new event, and it's the one that yesterday I named double-double. So something interesting is that for a tau decay process, you actually know, remember that if you have a tau neutrino, makes a tau, this makes a blob, this makes a blob here. I know the inelasticity distribution. Remember, the inelasticity is the fraction of energy that this lepton has after it has a DIS interaction. The inelasticity tells me the fraction of energy that comes here, basically, and then I also know the tau, how the tau is going to deposit energy when it comes out. And one thing that's interesting is to look at the difference between the energy of the second bang and the energy of the first bang. And this is known as the energy asymmetry. And so here, you see the expected distribution as a function of the energy asymmetry. So taus, here in green, like to have approximately a flat energy asymmetry. Whereas things that are not taus, things that are just a single blob or a track, tend to have energy asymmetries that are closer to 0 or closer to 1. And what you can see here is that of the two events, one event here is in a region where the energy asymmetry does not really significantly prefer a tau neutrino interpretation, whereas in this case, you really want a tau neutrino solution. So this is the first event is Big Bird. That's the one that is in a bad region of energy asymmetry. And what you can see here is this is the big event. This is a multi-PV event. So this part of here was such a large event that the domes were totally saturated, so you cannot see anything there. But you can see kind of outside, and what each of these things tells you is the observed distribution of data hits. And you'll see that nothing looks very suspicious. On the other hand, event number 2 that I showed you yesterday in the colloquium is this one here. It's around 70 TVs. And we estimate the first energy loss produced by the tau CC and the decay to be around 70 meters. And in this one, it's not such a large event. So for that one, the domes are not, let's say, totally saturated, so you can look at them. And when you look at those, in particular, let's say this one here, you do see double peak structure. And you see not only in one dome, you see it in here, let's say here, to some extent there. Okay? So we see it because first we reconstruct the two energy depositions. Those are more than 10 meters, in this case around 17. And then when we look at them, you see these waveforms. So with that, like I showed you yesterday, you can measure the flavor composition. These errors are gigantic, right? This is allowed most of them. But one thing that you can think about is, instead of trying to look for astrophysical neutrinos and just trying to reconstruct the separation between the first loss and second loss, what about if you just go dome by dome, so detector by detector, and look for this camel-shaped structure? And every time you see a camel-shaped structure, you see like, maybe that's a tau neutrino. So you can do it too. And that's called a double pulse analysis. And the idea is very simple. You have a real tau. It interacts very close to a dome. So this dome here actually sees itself. The first light when the tau is produced, and then when the tau is decayed. So here is a picture from simulation of how that would look like. If you have an electron neutrino, an electron neutrino just makes a blob. It's like just a blob. A tau neutrino interacts very close with the detector, make first blob, second blob, and that looks like that and that. Okay. Let's skip this. A problem with this could be, if you have a muon. So a muon actually also is able to make multiple blobs. So the good thing about the muon is that it will continue. The muon energy losses are stochastic. That means that there's a chance that you have a muon, and it has a first loss, and it's quiet for some time. It has a second loss, maybe it has 2 consecutive losses, and it's quiet again. So it can fake that per signature. So you can look that's the first event, that's the double-double, so it looks like it has this nice camel shape. But I want to tell you what the dangerous part about looking for tau neutrinos in a cube is, and it's events like this one. So in this event here, this was picked out because one of the domes, among other things, had a very nice double camel structure. But in this case, we identify this as not being a tau neutrino, and the reason is that in this case, it's somewhere in the corner of the detector, where it could have been a muon that just went something like that, and it just has 2 weird losses. So to have tau identification and be sure it's a tau, you want it to be in the center parts of your detector or your clear ice pieces, so you can be sure it was not a random muon event that had 2 strange losses. Okay, so I'm going to stop here. Questions? I think we have 10 minutes, right? Or 5?
Yeah, we have 10 minutes.
Okay.
Which we're going to use anyhow, so just ask questions.
I think there's a question there.
So I think you explained it yesterday, but anyways, how do you choose the reality, and why do you expect to be Poisson distribution when you obtain the other values?
Yeah, that's a good question. So we pick it to be the null hypothesis on my baseline model. That'll be the standard model of my baseline assumptions. So this is the case when you have, for example, BSM search or a search of point sources. You're doing a discovery analysis, right? So you pick what you know is sure, or you're conservative. So you pick no source, no dark matter, something like that. It's more tricky, for example, when I'm doing an analysis, say like, I'm going to do it now of an analysis of a astrophysical neutrino spectrum. So now, that it's been measured but not measured out very well. So you pick something that was the previous measurement plus the previous measurement is how you will do it. That has some effects on how you do your statistics because it makes basically some asymmetry between that hypothesis and that other hypothesis. There is a procedure that you can do if you're concerned about that, if you think that that bias is very large, to go about it. And basically what you do is you not only construct the test statistics according to your null hypothesis, you construct it according to your alternative hypothesis too. And so if you are interested in that procedure, I will put it in the slides as a reference. We have a paper maybe last year that establishes how we do that in that case. And your other question was about the Poisson cases, right? So if you have a rare process, rare process, the number of counts of a rare process is well described or expected to be described by a Poisson distribution. Because neutrino interactions are rare processes in themselves, that actually applies here. So you could also make other choices. For example, some people will tell you that it could be a Gaussian distribution. That is true when the number of counts is large. The Poisson process converges to a Gaussian process, or to a Gaussian distribution process. Yeah, so it has to do with the fact that that's how you model rare events.
Okay. You said that the number of beans has to be more than 20.
The number of counts per bean,
counts
so
per
that
bean.
so the Poisson is approximately a Gaussian. So what you can do is, you have a Poisson Ck given lambda, right? So the probability that you see k given lambda for large values of km lambda can be approximated by the Gaussian formula. The Gaussian with some mean and sigma. So Gaussian actually, let me just be a little more clear. So a Poisson only has a single parameter, which is the rate, okay, and the observed counts. So when these are large, this will actually converge or be the same numerically than a Gaussian distribution. So this will be the same as this, but the Gaussian actually has two parameters, right? The first parameter is the mean, and the mean will be lambda. And the second parameter is the standard deviation, and the standard deviation will be the square root of lambda. This is the reason that when you are often including Gaussian uncertainties, when uncertainties be a Gaussian, people will tell you the error, statistical error, is the square root of your number of events. It's because in a Poisson distribution, the standard deviation is equal to square root of lambda, and the mean is equal to lambda. Okay.
Is there something we can do if the number is less than 20?
Then you use a Poisson
formula. Okay.
So how the double interaction of neutrino depend on the energy?
How does the neutrino interaction depend on energy?
Actually, the double interaction, like.
The what? Oh,
Yes.
okay. So the neutrino cross-section is energy dependent, so that's growing. And we talked about that thing on Monday, but basically at high energies, it grows like a power of the energy. I forgot what the power index is, but it's growing with energy. Okay. But your concern is, and the way it grows is the same for all neutrino flavors. But your concern is not only making a tau neutrino, but making a tau that comes of interaction that's visible, right? And so to make it visible, you need the tau separation distance to be large. But the tau distance, in average, is just equal to C, the lifetime of the tau, times the boost factor of the tau, and that's just equal to the tau energy divided by the tau mass. So it grows linearly with energy, the separation. And for us, the separation is related to detectability.
All right, so given that you have we're all very tired. Let's go for lunch. Thank you, Carlos.
No problem. Okay. No problema. Ok, esto hay que dejarlo.